Hello and welcome back to Precalculus1 sections 1.4 and 1.5. We're dealing with the linear functions, slopes, and rates of change. Now, these rates of change will be really upgraded in calculus using derivatives, and you'll get a lot more information, obviously. Right now, we are dealing with the basic ideas in this class. So we start first with the idea of a linear line, which you guys are used to as y equal mx plus b. That's not changing ever. That's what it is. And we know that this m is the slope, which can be computed as y2 minus y1 over x2 minus x1 if you are given 2 points. B is the y-intercept, and that would be 0, comma b as a point. It's always on the y-axis because it's a y-intercept, right? Common sense in the naming convention. So y equals mx plus b is the linear line. You know this from algebra. What else do you know from algebra? You know that this can be converted into what some people call standard form, ax plus by equals c, where a and b are integers. So that's another. So you can't have fractions or decimals there. They have to be whole numbers. And then c can be anything. So that's another form. I would say less important, but then whatever. And then we also have the point slope formula that we can use to compute the equation of the line, which was y minus y1 is equal to m, open parenthesis, x minus x1. This is more of a procedure because when you plug in numbers for y1 and x1 and compute, you actually end up with y equal mx plus b. So this is not a new equation for linear line. It's actually one that you use to calculate stuff. Now, to understand all of these equations visually, we draw a linear line, straight line. It's going to go through this value here, let's say number 2. And we are going to have the, let's say this point here, you can see that that point is 2, 3. If you count squares carefully. So I just put the arbitrary line and I'm just looking for intersection points. I didn't assign anything to this. So now, what is the line? What is the equation of the line? Equation of this line is going to be the one that goes through to both of these points. And we can find the slope m because we do have 2 points. I do have 0, 2, and 2, 3. So those are your x1, y1, x2, y2, which you can plug into the formula. You get 2 minus 3, right, divided by 0 minus 2, and you get positive 1/2. Now, you already have your y-intercept. This is a cheap problem. Y-intercept is given, so you don't have to go through any horror calculations. All you need to do is to now just write y equals 1/2 x plus 2, because 2 is already y-intercept. It goes through 2 on the y-axis. Bueno? Good. So we have equation of the line given. Now, when these calculations are a little bit trickier, you might remember from algebra, then you might want to use this formula. Say that you know that slope, so find equation of the line given m equals 1/3 through the point 5, 6, right? So now this 5, 6 is not 0, b, so 5, 6 is not y-intercept, therefore we have to use the y-intercept form. Sorry, near the y-intercept for the point slope form. There we go. So what do I have? I have my x1, y1 given. I have m given. So if I write y minus y1 equals mx minus x1, I just plug values in. So y minus 6 is equal to 1/3 x minus 5. And just simply by multiplying and doing the common denominators, we immediately have the answer. So y minus 6 is equal to 1/3 x minus 5/3. Add 6 to both sides. And we have y equals 1/3 x minus, actually will be plus, because now you have plus 6. So that's 18 minus, so plus 13/3. When you do the common denominator, you get negative 5/3 plus 18/3, which is positive 13/3. And there's the equation. So we used point slope formula, and you see it's not a new formula for linear line because you end up with y equal mx plus b. The point slope formula is the procedural formula that you use to calculate the value for b, for y-intercept. If you want to graph this, again, you might say, oh my god, 13/3. It's 4 1/3, right? Not a big deal. The first number that it's less than 13 that you can evenly divide is 12. 12 divided by 3 is 4. So this is 4, and then you have 1/3 left over, so it's 4 1/3. That's actually very easy to graph. So you start by graphing the y-intercept, which is 4 1/3. So 1, 2, 3, 4, and then 1/3 is somewhere over there. And then from that point, you count the slope 1 up, 3 over. So if you started at 4 1/3, 1 up will be 5 1/3. So 5 1/3, and then run 3 units to the right. 1, 2, 3. This is where the line is. So you can graph the line once you know the points. So note that it didn't end up having what you call a nice number for y-intercept. Doesn't matter. All of the numbers exist on the y-axis. You can have pi, 3.14. Hopefully you don't have pi, but it could. So 13/3, again, the reasoning was the first number that is smaller than 13, that it's evenly divisible by 3, and that's 12. 12 divided by 3 is 4, so it's 4 whole units, and then 1/3 left over, so 4 1/3. Once you are at 4 1/3, you have to go rise 1, run 3. Well, from 4 1/3, rise 1 to 5 1/3, and then 1, 2, 3 squares over. Have you figured out yet that the square notebooks are godly in this class? Not yet? Stay tuned. You will regret every class that you are using the lined paper, because lined paper will not be providing you with the grid that it's evenly spaced. So the graph are going to be crooked and it's going to be difficult to see. You can get a notebook for the same price, except it's a square notebook, and then you can have these graphs straight. Note that I have the grid in the background. This is not, oh, it's a professor's tablet. No, this is a tablet where I can change it into anything else. But all other backgrounds are useless because the graphs become crooked and then useless. So look into getting the square notebook. They look exactly the same. They have a spiral or glue or whatever. And that way your graphs are going to be easy to understand. Also for me, to label the graph and score maximum points is easy because the coordinates of this point, I just count the squares. So for x coordinate, 1, 2, 3, perfect. And for the y coordinate, 1, 2, 3, 4, 5, and a third. There you go. So I can just look at the grid and count, both to draw or to get information off of it. Cool. So that's all of the stuff that you know from before, from your algebra. All of this stuff is in your 1.4, which was skipped. I would add maybe one more. Actually, no, there's something else that I want to talk about, and that's a notion of, this is very important, vertical and horizontal lines. So in section 2.6, right before second exam, if you choose to have one, you are going to run into notion of vertical and horizontal asymptotes. And those asymptotes are actually vertical and horizontal linear lines. It is very important for you to remember that if your graph looks like this, you know that you have an equation y equals to 2. Because if you look carefully, it's a horizontal line through y equals to 2, and x is not mentioned in this equation whatsoever because this line takes on all values of x from negative infinity to positive infinity. So horizontal lines will have an equation y equals to a number, and it goes through that number on the y-axis. The vertical equation, let's say this one, going through negative 3 would be x equals negative 3. Again, observe there is no mention of y in that equation because y assumes all of the values from negative infinity to positive infinity. X is fixed to be negative 3. I can move this to negative 1. It's no longer negative 3, right? So I can move it somewhere else, but it becomes a different function. So only y values for the vertical situation, right? So, and I just noticed that my title and the pictures are there we go. Fixed, right? Fixed. Good. Slopes. Still 1.4. This is actually peaking into one. I believe that the schedule says 1.5 second half only, which is the word problems. They're skipping the first half of 1.5 as well, which is the story of slopes, which you know from algebra. But then, maybe it's just slope. How about that? Slope. So we already know m is equal to y2 minus y1 over x2 minus x1. We know that. And hopefully, you also know that if the function rises to the right, slope is positive. If the equation falls to the right, then it's negative slope. And you also have the horizontal line through some number c whose slope is equal to 0. Let's do some experiments. Behold the round object. We all see that it's a round object. What is going to happen as I place this object on the surface that it's not sloped? Is it going to roll? No. Round objects do not roll on non-sloped surfaces. The equation for the surface of this desk in Calculus 3 is z equals 3 because it's 3 feet high. All right? It's about half of my height, so 3 feet, right? But that's in Calculus 3, 3D mathematics and so on, the plane, the surface of the desk, the plane, entire plane, we call that value, we call that variable z. But anyway, if you want to now take the same equation and put it in Precalculus1, you will not look at the surface of the desk, you will look at this edge, which is a line. And that's where the algebra lives. When you have this line is parallel to the floor, which is your x-axis, which means this is a horizontal line. Horizontal line with a slope 0, marker doesn't roll. As soon as I put this on a sloped surface, which is, this is surface, literally a surface, right? We introduce the slope. As soon as we introduce slope, round objects will roll down that slope. Now, if I increase the slope, it goes faster, right? Physics, gravity, and everything else, if you're interested, we can talk about that as well. The object will not roll on the horizontal line. Object will roll whichever way is sloped. You can calculate that slope as rise over run. And you can see that the bigger the slope, bigger rise you have, and a smaller run. The shallower the slope, more run, less rise. These are the concepts that you actually sit and think about to connect them. There's one more situation. So we have positive slope, negative slope, zero slope, and what other kind of slope? Yes? Undefined slope, also known as infinite slope. See, this board is vertical. So this surface here, in Calc 3 called y equals, let's say 0, beginning of the universe right there. If I place a round object on it and let go, is it going to roll? It's not going to roll. It's just going to fall, right? One. So, if I put the object here, let go, it falls straight down, it doesn't roll. The slope does not exist. Or you can say slope is infinite. Now, if you are to put all of this onto the xy plane, you can see the story of evolving slope. Your slope starts, let's say, as a zero slope, m equals 0. And then you know that your equation y equals x is a 45-degree line, right? 45-degree line goes through the middle. For y equal x, what's the slope? What's the slope? For the equation y equals x. What's the slope there? 1. So look, m equals to 0 is on the x-axis, and m equals to 1 is here. And then this is your m equals 2. M equals 3. M equals 4. Do you see how the numbers start at 0? And as the line tilts this way, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, infinity on the vertical. See how the slopes work? You can have a half slope. The negative slopes are going to do the same thing, except they're going to go down. So negative 1 slope at 45, and then negative 2, negative 3, negative 4, negative infinity. All the way to undefined slope, which is infinite slope. So now you use the slope to calculate the pitch of the roof, to calculate the pitch of the roads. The roads, when they are designed properly, are actually calculated, let's say 78 and so on, to look like this. This is exaggeration, obviously. So your middle lane is here, and your left and your right lanes are there, and this is the emergency lane, right? Why is it designed so? And the cars will be going this way, right? There's a wheel and another car, right? So why is it designed this way? So the cars actually drive into the, right? This is a cross section of the road. Why is it designed this way? Water runoff, right? Because if we would like be like this, you would have a lake in the middle of the road. The least amount of water on the heavy rain should be, if the road is properly designed, in the middle lane, right? Because all of the rain that falls, right, down everywhere, it's going to run off this way, it's going to run off that way. Those are the slopes, right? Now we can have a parabolic design. We'll see a problem, I believe, somewhere in 2.2. Or it could be the straight pitch. Usually you use the straight pitch for your patios, right, around the house, the gutter drain, and so on. Because you're not going to get the rain right at the roof. Just go into the basement, right, of the house. You collect that in the gutter and you put it in a runoff pipe and put it some amount of feet away from the house. All of those calculations are slope calculations. When they say, you know, you drop 1 inch for 3 feet. Slope. That's 1 over 36. If you want to transfer that into mathematical equation that we had. Because 3 feet times 12 inches is 36 inches. So 1 inch of drop for 36, right? So it's rise is 1, rise is 1, and 36 is the run. So rise over run, 1 over 36. You also drive around and you might see that the signs with the triangle and a truck on it. It says 10%. That's for truck drivers. They need to know the steepness of the hill. Maybe the cargo in the truck is not tied down. It's going to roll out of the truck, right, on a heavy pitch. Also, they need to know which gear to be in as they drive up or down the hill. So those signs. Now that 10% drop-off is actually slope simplified, right? For every 10 feet, 1 foot drop, and so on. So there is a lot of, there are many applications. And each situation looks unique, but mathematically it's the same problem. So just take a look at what it looks like, whether it's a roof or a water runoff or a patio. It's just talk about a slope. Also, if you go skiing, you ski down the slope and so on. So that's the story on slope. And the actual part of pre-calculus and learning is to put this slope, which measures the change, to put this slope in a different framework. We are going to talk about rate of change. Which is that 1.5 part from the syllabus, which is assigned in this course. And we are going to actually use the formula for the slope, and we are going to modify it with our function notation to make more powerful formula, which we can use to approximate and calculate things. So the average rate of a change of a function. That's the actual title. So the average rate of change of a function is going to be given by change in y over change in x. This triangle thing is read as delta, which is a capital D in Greek alphabet. We also, but we call it change. And this is going to be f of x2 minus f of x1 divided by x2 minus x1. Notation, triangle, read as change in. For those of you interested, it's actually delta, which is capital D. Derivative eventually in Calculus 1 emerges from this. Now, how's this related to slope? Well, on day number 1, you will recall that y equals f of x. Now, wouldn't you agree that this is then y2, and the next one is y1? So there's your y2 minus y1 over x2 minus x1, which is the slope. So we can say because y equals f of x, we can replace y1 equals f of x1 and y2 equals f of x2. So we are replacing those values for y1 and y2 and use function notation instead. That's the only formula. It's the same as the slope, which uses the notation of the function on each y. All that's left is the word problems. Who loves word problems? Exactly. Which types of problems are the most important problems? What are the actual problems that exist? The only problems that exist are the word problem. When you sit in a meeting and there is a problem, it's a word problem. When you're trying to figure out how much money you make, how much taxes you're going to pay, it's a word problem. It's always a word problem. There are no problems. You will never see a problem from Precalculus1 when someone says, okay, your function is x squared. That doesn't happen. And it doesn't happen because we have computers today. Computers compute things. Your job is to model. Your job is to look at the graph or look at the physical whatever thing in the world and write mathematical model which computer will compute for you if you need values. You look at a stock option and you determine that it's losing or gaining money, and then you can maybe predict how much over in future you're going to gain or lose by looking at the trend, functional trend that's available. So your job is to actually only solve word problems. The rest is garbage. And unfortunately, we only have maybe 3 or 4 sections that deal with word problems in this textbook, which means 95% of the course garbage, right? Well, no. Pre-calculus is extremely important because of sections 1.6, 1.7, and 1.8, which drive all of your stuff later for graphing and everything else. We'll see when we get there. Become friends with word problems as soon as you can, because that's what the job is. You working out word problems, figuring stuff out, critical thinking, and so on. So let's just do the cheapest possible problem. So find the average rate of change of f of x equals 2x plus 3 when x1 equals 2 and x2 equals 3. You have the formula, just plug it in, see what the number is at the end. So what do we get? We have f of 3 minus f of 2 divided by 3 minus 2. All we do is we plug in the values. So f of 3 is 2 times 3 plus 3 minus f of 2 is 2 times 2 plus 3 divided by 1. We don't have to worry about that. So I have 6 plus 3 is 9, minus 4 plus 3 is 7. The answer is 2. Just plug and pray. It works out. All it is. Can I make this hard? No. Can I make it annoying? Yeah. We're going to learn the difference in this class, if you haven't learned so far, between hard and annoying. It's going to be a lot of annoyance, right? How do I achieve that? I put some fractions around and, you know, things like that. Then you have to chase common denominators and things. Can't make it hard. We are going to learn one equation, and then actually no, that equation shouldn't be here. It's not. Okay. Good. So yeah, let's take a look at word problems from the textbook. They only give you 3 problems here, so let's go with the first one, and then you can do the rest at home as practice. All right, so, oh, you can't see it. There we go. So this is on page 226 in the textbook. Again, you don't have to drag the textbook anytime I want to show something from the textbook will be on the projector. So we're looking at that graph over there. The graph shows the percentage of total spending in the United States on food and healthcare. Food is here, healthcare is here. We see that in 1950, right, 60 years ago, so almost 70 years ago, people were spending 3% on healthcare and 22% on groceries, right? So you spend 25% of your income on those. In 1970, spent 16% on food and 7% on healthcare, so together 23%, right, went for those. And then another 23, and another 23. So this one was the 25. Observe also the trend that as the years go from 1950 to 2010, which is only 7 years ago, people are spending less percent on food and more on healthcare. Why? What happened? Exactly. See garbage now, McDonald's and all that nonsense. Right? It's really cheap, but it's bad. So we need to cure a lot, right? You see that? It's a direct correlation between the things. So the more money, right? The less money was spent on food, cut corners and get the GMOs and get all of the processed food and food that tastes good, right? Because everyone's like, I don't like broccoli. It's okay. You have health care, so you can go and undergo surgery. Broccoli or the knife. Right? I know. So go home and hate it more. The doctor was just going, oh, there's no broccoli here. Awesome. And then they cash in the check. So, and such is life, right? So, what do? You have points in time on your x-axis, which is 1950, 1970, and so on. That's your x1, x2, x3, x4. And then you have y values, 22, 16, and so on. You have points that you can use to determine the line, the linear line which models this trend. So you can draw a line that approximates something like this. And then you can infer, right, about the future or peek into the past. You can also do the same thing on the other side, right? And say, at some point in time, right, we're going to spend 0% on food and 100% on healthcare, right? We'll see. But you can use these values. So remember how you need to have x1, y1, and then x2, y2 to find the line. So 1950, you can also renormalize this. You can say that 1950 is year 0, because that's when we start measuring all of these things. And then this one will be 20, 40, 60. It's much easier to calculate with 0, 20, 40, 60 than to calculate with 1950, 1970, right? It's much easier to renormalize this. So now what are your data points? Your data point would be 0, 22, 20, 16, 40, 10, 60, 7. You have data points. So pick 2 data points and create linear lines. It's a very simple concept, right? When you think about it a little bit and see what's happening. So here, let's say this one and this one. Find the linear line through those 2 points. So I'll catch up on the tablet with this stuff, and then we'll solve it together. So this is problem, I don't even know what the problem is. It's something. You all have negative 3/10? What happened? Just to relax. Well, now you can find the line after that, because you have your 22, which is the y-intercept, because x is 0, right? So as soon as your point is 0, comma, then that number must be b, and that's the y-intercept right away. So there you go. Yep.
Okay, so where did you get the 22 from?
From the y value. 10 minus 22 40 minus
y1.
y2 minus y1 over x2 minus x. So once you have the model, the y is going to be the percent, x is going to be the year, and you can compute things with a model. So you can predict for 2017 by simply plugging in 67 there, right? Because the x's are years. This is 1950. So 2017 would be 2017 minus 1950, 67. So if you want to see or approximate how this graph is doing today, you will place 67 here, and you will see what is the amount that people spend on food and what's the amount that people spend on the. Right. Well, this was just the food side. So we would see what's happening on the food side. So for the percent in 2017, we say 2017 minus 1950 is equal to 67. So y equals negative 3 over 10 times 67 plus 22. This is going to give you a number. Right, so 180 plus 21, so that's 201. Just call it 200 divided by 10. 200 divided by 10 is 20, right? So we have negative 20. So about negative 20 plus 22 equals 2%. If it continues falling at the same rate, right, that we computed from this, the model predicts that today we should be spending about 2% of the yield. Now, obviously, that's not true, and it's definitely not true for those who eat healthy. Great. We can also calculate the rate of change. So let's calculate the rate of change. For the same problem, using the same numbers, rate of change would be 10 minus 22, which is, well, negative 3 over 10. Now units for something like this are very important because that's how we understand the word problems. And the units for this would be percent per year. So -3/10% per year. You want to analyze this, you are, look at this, guys. You're losing 3% every 10 years. Lose 3% every 3 years. That's how you interpret this. Yes, every 10 years. Lose 3% every 10 years.
Okay.
3% of the money that you spend. I mean, not you don't lose it. You spend 3% less. That's what I meant. Then, right? So, statement is spend 3% less every 10 years. That's what that statement, that's what it means. That's why we calculate that. So I know that roughly every 10 years it should drop 3% out of the percentage that we have allocated for food. Which means that in 2 years and, sorry, in 23 years, by end of April, we don't get food anymore. Yes?
Okay. Can you explain again over there? Because I cannot see the graphic here. So you say 2017, and this is the graphic pretty much. The 1960.
Aha. Okay. So the graph, one more time. Right, the graph shows that in 1950, the graph has data from 1950 to 2010. Now we are going to, instead of writing 1950, we're going to use 0, and then plus 20, plus 20, plus 20, and use 0, 20, 40, 60 for calculations rather than these. Can you use these? Sure, but then calculator and manual instant computation. Fine. So when I use 0, 20, 40, 60 with their associated percent values, I get the data set, and then we pick 2 points, first and whatever other, right? And with that information, you have 2 points in space. You're able to draw the line to find the equation of the line that goes through those points. That line will have a slope, and a slope always has the units of y divided by x. Now y was percent, and x was the number of years, so it's percent per number of years. Our slope worked out to be -3/10. -3 means drop 3%, and then you have 10 in the denominator. You call that every 10 years. So our slope of -3/10 has the interpretation that we are going to spend 3% less money on food every year, every 10 years. So for the next, right, for the next piece of the graph, this should be much smaller, which it's already way too small, but it is what it is. Okay. That's it. I hope you're not disappointed. If two lines are parallel, describe the relationship between their slopes. Very good. Perfect. Same slope. How about perpendicular? Yeah, negative reciprocal. Good. If you know a point on the line and you know the equation of the line perpendicular to its line, express how you write the line's equation. Let's see your algebra question. Because you pick the slope, right? You flip the slope and then use the formula. So all of those things, there's a lot of stuff in here that you can read and then relearn if you're missing any of these concepts from before. Sounds good? All right. Questions, concerns? Nothing?
I have a
Yes.
question, yeah. When you have the formula here, how do you find the develop between, for example, sorry, the graph over there, what's between the two?
Well, in this case, anytime you have a 0 for x, the other number is immediately b, because that's the y-intercept. Because x is 0, that means you're talking about the y-axis. Whatever number on y must be, right, must be that. So, yeah. If I didn't have the first point, then we would have to use one of the formulas to calculate. You can use the slope-intercept formula. You have the slope, and you plug the point in, the one that I reviewed. This one, point slope. Yeah, can't see. There you go. So if you don't have a ordered pair that starts with 0, you don't know what b is. But then you can use that formula. You know the slope, and whatever point you are picking here, that's your x1 and y1. When you solve the algebra, it comes out on the other end. Cool? Good. Anything else? No? Okay, good. Otherwise, it was either a question or push-ups, but I guess. No, don't push-ups. Everyone does push-ups.
The question I have is, for the exam, for example, to have something like this, okay? Well, the way that the computer and the program is teaching is like, you have to put all the points for x first, and then find the y. You have to do all these and then graph, or you're okay for something you can do right away?
Well, it depends on the level of the knowledge, because plugging points for x and computing y's and then connecting the dots is the method that works for every function under the sun to graph anything and everything, but it's the most tedious and the slowest of all. That one is always available because you can pick your x's, -10, -9, -8, -6, right? And go all the way from -10 to 10, compute 20 points, right? And plot those and connect them. Or you know how to graph base functions, and then the next class on 1.6 is how to shift and change and compress and flip and all of these kind of things. That's next class. So which way you're going to do? We are still working with the basic graphing because you are only working on a linear line. But starting Tuesday, we are introducing the graphs that are on the cover of your textbook, which is all of the, so you have the linear, quadratic, cubic, square root, exponential, logarithmic. Now, exponential logarithmic graphs will not show up to the third chapter, but the concepts that we learn in 1.6 apply obviously to that, then applies to PreCalc 2, trig, all 6 of those, and so on. So if you don't know how to graph, you will have to go and waste time working on the points. Assign x's, compute y's, you have ordered pairs, plot those, connect the dots, and you're done. But again, get the square notebook so those graphs are meaningful and you can actually learn from that experience. Anything else? 10 minutes of push-ups, not that bad. Yes, there
So for the homework, we don't have to do all the problems online. We can just do whatever to get the concepts.
yeah, that's what it is. You can do them all. You can do half. You can do. See, the trick is that the homework is your exercise, your practice, which will emerge at the exam, right? Your knowledge and the prep. Mathematics is the same like running. The more you do it, the better in it you are, like everything else in life. So if you are if you need 5 problems, it's 5 problems. If you need 10 problems, it's 10. Everyone is different. Let me just end this. I don't want to forget this to run, so bye stream.